Where we left off on Monday is we were just kind of finishing up the while loop and the do while loop examples. And I kind of mentioned that do while versus while isn't that important of a distinction. It's just another way to kind of reverse the order of the loop body versus the code that checks whether we should stay inside the loop body. But the general structure of the loop remains the same, which is we have some variable that allows us to ultimately be initialized and then check whether some condition is still being met. So you need some code that creates the variable for our loop, some code that's checking that variable within our while statement, and then, although in this example of the do while it's kind of hidden, it's still there, some code that updates that variable inside the loop so that at some point during execution, the loop goes from having the condition be true to the condition no longer being true. We stay in the loop to we no longer stay within the loop. We also then talked about the floating point example and had a little bit of fun with that on Monday. I think the main takeaway is just have care when doing comparisons and equality checks with if statements and certainly with loops with regards to floating point, because this concept of mathematical precision is a little bit more subtle once you're dealing with any programming environment for which we have a finite amount of storage for those floating point variables. We can't always precisely represent exactly what we want. So the way we refactored this code briefly on Monday was to not check for an exact match, but to check whether the result we calculated was within some reasonable error tolerance of the value. And you'll generally want to do that when dealing with floating point. For if statements, that's the case. And then for our loops for which we are checking equalities, we also would likely want to do that for our floating point. So that's the while loop. That's the basic structure for our looping. And we also then, as you've already seen in some of the programs you've been playing around with, we have the for loop construct as well. Again, the three main components that are found in our loops. We have some variable, some expression that initializes that loop control variable. We have some relational operator that we're checking periodically, repeatedly, to continue or not continue inside the loop. And then at some point, there needs to be some other expression that updates that loop control variable. We have all three of those things in our while loop. The only point of the for loop syntax is it just a more convenient way or a more explicit way to list all three of those components that all of our loops are required to have. So if we think about our for loop, while it sounds and it seems a little bit different, that's all that it is. It has three components to it, and they're all just put within the parentheses here. So we have a for loop where we say, for some initialization of a variable, while some condition of that variable remains true, and every time through the loop, update that variable based on some way we want to update to update our loop as we go. Then inside our curly braces, then do something, then repeat some operation here. Otherwise, it's exactly the same. And there's always a correspondence and equivalence we can make between a while loop and a for loop and a for loop and a while loop. There's nothing we can do with one that we can't exactly do with the other. There just tends to be certain code patterns for which it makes maybe more logical sense to encode our loop with a for loop versus with a while loop. And again, there's no wrong answer in terms of which loop structure you choose. There's not a bug or a mistake you're making, but I would say in general, if you know you're looping a finite amount of times, I want to do something 25 times. Or I want to do something n times, a counting loop. And we usually can tell it's a counting loop when we have that I plus equals 1, or I minus equals 1, or I plus equals 2, that we're having a loop variable that we're just incrementing or decrementing by some amount. Usually the for loop allows us to encode that a little bit more cleanly. That's more of a general pattern than a requirement. Whereas we have a loop that's going to continue until some somewhat more arbitrary condition is being met, where our variables are also being updated in one or multiple ways, then maybe the while loop makes more sense for that purpose. But it's never one or the other. It's just a matter of which one we wind up choosing that makes it easier for us to write, debug, test, document our code here. But our for loops do tend to look like that, where we have for I equals 0, I is less than 25, I plus equals 1. But again, that's exactly what we could have already done with the while loop. We have our loop control variable that we just, for historical reasons, call I, J, K. If you're more than 3 for loops at a time, maybe it's time to rethink your code, but it's pretty common to have 3 nested for loops, I, J, K. If you have to start going to L, M, N, O, P, that's not a great sign. But that's just for historical reasons, and it's a habit that people still generally follow. That if we have a loop control variable for a for loop and it's a counting type of for loop, we just call the variable I. You don't have to call it I, but that's just what we tend to call it. But in this case, I is our loop control variable. We have an explicit statement that initializes I. We could have initialized it at the time of declaration, like we sometimes have been doing for our while loop examples, or inside the for loop itself. That's what that first part before the first semicolon is saying. I'm entering the for loop. First thing I do, I initialize I to 0. Then we have our while condition. We repeat this loop for as long as I is less than 25. That is equivalent of having while I is less than 25. It does, in fact, check that condition right away. So it's more like a while loop than it is a do while loop. But in general, it does what you hope it would do. Initialize I to 0, loop while I continues to be less than 25. And then, although maybe it takes a little time to kind of read code in this fashion, we then have what happens once the loop has completed one body. We've done the code inside the loop once. In this case, we're incrementing I. We're updating, and you would generally want to, in some way, shape, or form, change your loop control variable each time through the loop. In this case, we're incrementing I, so this loop will be a loop body that executes exactly 25 times here. This code example is not itself terribly interesting. In this case, it's entering a character C, and it's just going to print out the character, in this case, 25 times. And as a debugging mechanism, for our for loop, it's very common to want to print out, certainly if things aren't working, I'm on iteration I, right? I'm on iteration, in this case, 0, then 1, then 2, then 3, then 4, etc. And it's just printing out the character we inputted each time. This is using a less commonly used feature of C. I guess I was bored when I put this example together. We know that % is our format specifier, where we want to print out a character or a string or an integer. We can specify when we print it out how many how many characters do we want to use to print out that value. By default, it'll print out as many as are necessary. If it's an 8-digit integer, it'll use 8 characters for it. You can also explicitly say, hey, no matter how big the integer is, I want to use 8 spaces for it. And it'll pad it, in this case, with blanks before it. If you want to pad it with zeros, you would do 0, 8. This feature we're using is saying, provide as an input how many characters, how many digits I want to use to represent this print that's corresponding to that %C here. So in fact, iteration I, in this case, I'm going to print it I characters wide, and I'm going to print the same character each time. We'll enter in Z for Zambrino, and it's going to be printing out our Z. So for 0, it doesn't really work, because 0, it needs at least 1 digit. And then it's printing it out as 1 digit, 2 with some white space, 3, etc., up to 24 at the very end here. This is just an example of something executing 25 times. It's not terribly interesting, but just to show what happens, that there's nothing really magical about the for loop. It is exactly the same as what an equivalent while loop would be doing. We had a loop control variable I. We initialize it to I equals 0. We iterate until I is no longer less than 25. Each time through the loop, we increment I. So at the very end, just as kind of a test to see what's happening, we print out the value of I, and it prints out that I is, in fact, 25 by the time the loop is complete. Questions about this example? Because getting to know the for loop syntax is important. We'll be writing a lot of for loops this semester, but there really isn't any more to it than that. You may find code examples that are trying to be clever with for loop, and here I would say let's Let's avoid unnecessary cleverness. But there's nothing that requires your loop control variable be called I. There's nothing, of course, requiring that your variable be initialized to 0 and that it be checked against a particular constant value here. You can do whatever you want for all three of those components of the for loop. Anything that is valid C can be part of the initialization, the boundary check, and the update statement as part of your for loop. So that syntax here is valid. It's dumb, I guess, right? There's no point in having a for loop if it's going to look like that. If you really have some truly arbitrary looping conditions you're interested in, then a while loop probably still makes more sense here. But you could have a scanf be what initializes I. It doesn't have to be checking a particular value, and you can do I mod equals 12,346. Those are all valid. You can actually skip any of those components entirely. So if you wanted a very traditional while loop, but you just didn't feel like typing out the word while, you can skip the initialization variable itself entirely. You can skip the increment operator or the update operator as well and just put it inside the body of the loop. And then you basically have while I is less than 255. That's valid. It's not typical, it's not a traditional use of the for loop, but it's perfectly valid. So you can put whatever you want there. I think in general, when you have a straightforward, repeatable segment of code, it makes sense to use the for loop. And when it's not a straightforward, repeatable segment of code, you're not counting things as you go, then a while loop probably makes more sense. You can skip all the components entirely. You'll see code that does this. The equivalent would be while one or while true, which is a loop that you don't do anything when you enter, you never check to exit, and you do no incrementing as well. That would be an intentional infinite loop in your code that once you enter that for loop, unless there's some condition that, as we'll see, allows you to explicitly break out of that loop, you're going to stay in that loop forever. Very common, as we've already seen, for many of these for loops, you'll have you increase or decrease a variable by 1 each time through the loop. That's our I equals I plus 1 or I plus equals 1. We talked about how some of the design decisions for the C programming language were from an error in which saving a couple keystrokes or saving a couple bytes of code were an important consideration. So there's two other operators that I think you've already seen in some of these Zybook examples, but here is where we'll most likely use them in our code. That's the increment and the decrement operator that does effectively exactly that. Increment operator takes a variable and adds 1 to that variable. Decrement operator takes that variable and subtracts 1 from that variable. You can use these operators just by themselves. You can use I++ as its own line of code, and it'll increment the value of I. It is equivalent to writing I equals I plus 1 or I plus equals 1. You can also use the increment operator and take the result of that increment or decrement and use it to assign another variable. It can be on the right-hand side of our assignment operator. And in this instance, you can use the increment both before the name of the variable, that's the prefix or prefix increment, as well as after the name of the variable. That would be a postfix increment. This is a subtle point. People who teach C programming teach this to show how clever they are. I would argue the postfix is a much more common way we use this, but they're both valid. In postfix increment, we use the value of the variable for the assignment first, then we increment the variable. Whereas in the prefix increment, we increment or decrement the variable first, then we use that updated variable for assignment. So they look very similar. The end result of C after those two lines of code, if it was one or the other line of code, the value of C afterwards is the same, but the value of D afterwards is different between those two lines of code. In this example, the value of D has what C was previously. In this example, assuming again it's one line or the other, we're switching between the two. In this example, the value of D is the incremented value of C. It's a little subtle. It's sometimes hard to imagine scenarios in which we really want to do one of those versus the other, but you will see this in code that you review, that sometimes we know we want to do two things. I want to increment a variable, and I also want to take that variable and copy it to another variable. Other times, I want to eventually increment a variable. I want to take the current value of that variable and assign it to another variable. These two operators, putting the plus plus beforehand or putting it afterwards, gives us those two different effects here. Here's a really dated picture of Bjarne Strusup saying, when he sees that C++. So anyone here familiar with C++, or at least knows that it is a thing? We talk about C++ as like the next language after C in some sense. That's programmers thinking they're quite clever, right? So C++ gives us the next value after C, right? So whatever C is, we take plus plus as the value afterwards. That's why that exists here. But otherwise, this can lead to some pretty subtle bugs in your program if you're not careful. Again, I feel like sometimes these examples are there just to show off how clever we can make our programs, or unnecessarily bug-ridden we can make our programs. So if we start off with the value of A is 3, B is 4, and then we have a variable D here. And we have the assignment operator is D equals A plus plus. After that first line of code, what will be the value of A? That first little 2-line segment of code, what will be the value of A? It'll be 4, because we are incrementing A. The value of B? Okay, I don't want to hear from everyone. That's fine. B doesn't change yet. B stays 4. What will the value of D be? It could be 4. This case is 3. And that's the only point of this exercise. So that's fine, right? D equals A plus plus. Another way to read that is D equals A and then plus plus, right? So D equals the value of A and then we plus plus. Versus this next example, and I think if you have this, then we don't have to belabor the point. Now if we do D equals plus plus B, value of A has not changed. Value of B after those 2 lines of code is what? All right, you've got it. I want to hear from others on the next one. You got it. That's good. I'm glad you have it. Happy for you. B is 5. Value of D is going to be what? 5. Because in this case, that's the difference between those two examples, right? The other one was A++, which everyone's grade in the class is going to be. That one is plus plus B, which means we plus plus first. We increment B first, then we assign that to D. That's our prefix increment here. Next one. D equals A++ times plus plus B. If you start to have code that looks like this, you're really you're trying too hard. Split it up into multiple lines, right? Who are you trying to impress when you write that code? Value of A after that line of code is, it was 4. We're following it sequentially here. So it's now 5. Value of B is now 6, because the plus plus does happen after we're done with this. Value of D is now, someone said it quietly. I believe in you. Say it again. 24, thank you. Value is 24 because A is the previous value still, 4. B is the incremented value, 6. So 4 times 6, get 24. We do D equals A++, but now we print D is this, and we do plus plus D. You will see this in code sometimes where people are just trying to save a line of code, and in printing out the value, they actually are also doing some work on that variable. I don't think it's a good idea, but you will see this in code, just trying to save a line of code. So D equals A++. A is going to be 6. We've incremented A. B is going to be 6. B is not going to change. What is the value that gets printed out for D here? It's going to print out as 6. And then finally, this last example is an example of undefined behavior in C. If you have both the operator and a prefix increment operator, the C standard says it's kind of up to the compiler to determine what happens to A when it's being used mathematically. Afterwards, it's going to certainly be incremented. So A is going to be 7 by the time we're done. We can say that for certain afterwards, but the value of D is undefined behavior as part of the spec. We won't belabor undefined behavior too much this semester. There are lots of undefined behaviors that if we're not careful, we encode in our programs. Comparing signed versus unsigned, dealing with overflow of variables as we go. This is another example of it where it's just undefined by spec. B is fine. D, actually, we can't say. It depends on what the compiler decides for us. Spec actually implies that if you write code that touches upon explicitly undefined behavior of the standard, the compiler is free to do whatever it wants. I don't see why it would do something terribly harmful, but it could say D is 39 or something. It could do whatever it likes for that example. Well, it's undefined just as spec because it's not clear what order the reading of this A and this A would need to be in your program. When we do plus plus A, that's prefix increment, which is increment A, then use the value of A. So that one's defined. But what value is this A supposed to be? Well, that's before, or whatever it was here at 6 beforehand. The answer is maybe. By spec, it could be. That seems like that would be a logical decision for the compiler to make. Just because we wrote a line of code in which this one happened before this one doesn't mean that this variable gets loaded from memory before this thing happens to get loaded from memory. So by spec, we can't say for certain what order those things are required to happen. And so that's what makes it undefined. And that's just an explicit kind of edge case. Again, if your code is doing this kind of thing, it's bad news. You will see this one on occasion in the programs we'll say programs that other people write along the way. I don't want you to lose sleep over these particular kind of prefix and postfix increment. For the purposes of our for loops, that is the most common time we would use those, would be to take our loop control variables, our i's, our j's, our k's, and because we're very often counting by 1, not always, but we're very often counting by 1, you'll have your I++ and your J++ as your loop update part of your for loops. Again, if you want to do I equals I plus 1, or now I plus equals 1, you're still very much allowed to. And this is the more common way you'll see this in the programs that you write here. And what this example also is just briefly illustrating is just like we've seen sort of chained or nested if statements is a very common thing we'll have in programs. Again, oftentimes you could take a nested if and rewrite it as a compound if statement. We've seen that. It's also extremely common to have nested for loops. Oftentimes our data has certain dimensionality to it, and we want to have a similar dimensions of our for loops to process data here. Again, similarly, we could almost always take a nested for loop and rewrite it as one more complex singular for loop, but it is very common to have these nested for loops in which we have a so-called outer loop. That's our I loop here. And then each time we go through the outer loop, as part of that outer loop, each iteration of the outer loop is an entire inner loop here. So each time through I, so 25 times through I, we're going to execute that J loop of size 10. The control and data flow graph, it can be hard to see that it's a nested loop, but that's effectively what's happening. Each time through I, we're doing the entirety of that J loop, which is initialize J to 0, check if J is less than 10, do a J++, and in this case, again, it's more of a debugging thing than any additional functionality here. Each time through now, the innermost part of our loop, we're printing out what our value of I and J are as we go. This is example nested loops here. And well, because this loop is kind of large, I have to scroll back up here. So we start with I equals 0. And then for I equals 0, we have the entirety of that J loop. You'll run into a lot of off by 1 errors as you write your for loops. And that's okay. That's just the nature of the bugs that you're going to see. But you have to kind of keep in mind that the most common version of these loops are these counting loops in which we oftentimes start with our variable at 0. We'll see why a little bit more next week, but for now, just assume that we count starting at 0 for historic reasons, but also because our variables are binary format, and 0 means like our initial value. So we oftentimes are starting at 0, and then we're wanting to iterate a certain number of times. So the value that that variable is going to take on if we want to iterate 25 times is 0 through 24. Maybe it's easier to see on the J loop here because it's inside. We want a J loop to execute 10 times, so don't overthink it, 0 to 10. But the actual values that J is going to have that we're going to see when we print it out are going to be 0 through 9 inclusive. Just count them up. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's 10 distinct values. That loop iterates 10 times. We don't write down 9 here. We write 10 here. But the actual value we ever see printed out is 0 through 9 inclusive. When J gets to 10, we're getting out of the loop. We're exiting the loop at that point, right? So you'll have off by 1 errors where you loop 1 too many times or 1 too few times, and just be ready for that. And really the best by far debugging mechanism for when that happens to you is exactly this block of code. Is when you're printing out your got this far code where like you're confirming your loop is actually looping like you're hoping for and you don't have infinite loops, that you actually print out the value of I and J as you go. So just remind yourself where you are in your code at any particular point in time. And you can then hopefully see the nested nature here. For I equals 0, we have 10 iterations. Then I equals 1, we have 10 more iterations. All the way through, we get to I equals at the very end here, 24, and we have our final 10 iterations at the very end here. Another extremely common bug is this one. You may not even be able to see it because it's kind of small on the screen that you're currently looking at. It'll happen to you. Happens to me. Happens to everyone. It'd be nice if the compiler would warn us or the linter would warn us when we've done that. For J equals 0, J less than 10, I plus plus. Well, it sounds stupid when you say it out loud, right? And so reading your code out loud is a good way to fix bugs. What's going to happen when we run that? Yep. And hopefully once you see that printout, you'll catch that you had that that infinite loop here. It's going to keep going. Don't expect it to do anything interesting. Right? What happens here? Outer loop is still probably okay. For I equals 0, I less than 25, I plus plus. This is explicitly a bug. For J equals 0, J less than 10, I plus plus. Well, we never actually change J anymore. So J stays at 0. There's never any reason for us to ever leave this inner loop, and we wound up with an infinite loop. That's going to happen to you as well. The off by 1 errors are going to happen probably more frequently, but the same debugging techniques that we've been following throughout are still going to save you here with our for loops as what they do for other loops. I think eventually this will become kind of second hand of just like you type out a loop and it works, but it can be a little tricky as you have nested loops to kind of keep track of where you are in your code. But let me just kind of forewarn you that most of the interesting programming problems you want to work on in life are going to involve multidimensional data. You have some data, it's an image, it's anything else that has multiple dimensions to it. You're going to be writing a lot of nested loops as you write programs in life. And so being able to keep track of I and J, planning things out in terms of what is the valid range for I, what is the valid range for J, recognizing that I have written a piece of code here that's going to execute that print statement 250 times for those ranges of I and J are an important consideration. Syntactically, it's really nothing too terribly new, but being able to problem solve in multiple dimensions is going to have to be part of your toolbox relatively quickly here. We'll get a lot of experience doing it. So that's my mediocre nested loop analogy, right? Think about like a car odometer, like an old school one, but conceptually it's still the same even with the digital one. Where you have like that inner counter that goes up until it reaches 9, and then it resets back to 0 as it increments the outer counter. It's exactly what's happening in our for loops here. The loops themselves are kind of independent of each other. The for loop could have other things as well. It doesn't have to just include the inner loop. Likewise, the inner loop can be doing all sorts of things as well. But ultimately, from the outer loop's perspective, you have multiple separate kind of invocations of that inner loop, and it's starting over each time through that inner loop. And that's explicitly what the code is doing. So think of this thing as executing the first time you enter into that loop, this check happening every time through that loop, and this plus plus or whatever increment operator you have happening once you've completed one body of that inner part of the loop. Let's try to see if we can finish up a problem-solving exercise in the time that we have here today. If it doesn't look good, if it looks bad, we'll fix it tomorrow. So an integer between 10 and 20 is our input, so we don't have to write a note on that. An output would be a well-formatted multiplication table for the range 1 less than or equal to x less than or equal to n. So if I provided an input of 4, although I said the input has to be the range 10 and 20, it would print out the following multiplication table. What kind of code structure would make sense for this? Nested for loop. It's not a coincidence, right? Another way to think about that is we have these values, and it's two-dimensional data. One of these can be our I loop, and then one of these can be our J loop. Printing tends to restrict how we solve these problems, because at least with the way we're currently doing printing, we'll learn another technique later this semester, but for the way we're currently printing, we're pretty limited to kind of left to right, line by line printing. So that kind of leads to a solution for which this is J, or this is the inner loop, because we have to kind of do it in order, and then this becomes our outer loop. So for I equals 0 to n, or in this case 1 to n, for j equals 1 to n, print the value of I times j. Getting it to look bad will be very quick. Getting it to look good will take a little bit more effort on our part here. This is example nested table. Fortunately, already kind of copied in what we sort of want it to look like. These are just meant to be spaces, not like underscores, but just to show that there's some proper spacing associated with this here. Input is n, an integer between 10 and 20. In theory, then your code should also be doing some error checking if n is less than 10 or n is greater than 20. Trust you already know how to do that. You already did a quiz today on that. We'll skip that part, but we'll do our enter in an integer between 10 and 20, and I'll pinky swear that you did it correctly. Okay, there's our printf scanf kind of prompt here. Now we're going to have our for loops. For now, because we haven't really talked about scoping yet, we'll also define our I and our j variables kind of separately. You could put it up top as well. That's been the practice we've been following a lot of this semester so far. The reason I'm waffling a little bit on that is because we're about to break that assumption come Friday. There's your advertisement for Friday. We're going to break the assumption about the scoping rules for our variable names. I see people jotting down in their calendars, be sure to attend class on Friday. It's kind of an important topic. You'll be fine. We have our for loop. This loop, well, there's more than one way we can do it. I look at this loop and I say, well, you know, it's 10 or n is 15, but it's not counting from 0. Let's say n is 15. We don't actually want to count from 0 to 14. We actually do want to count from 1 to 15. So there's nothing stopping us from doing that. So we'll start with I equals 1. It doesn't have to start at 0. And we want to continue while we're less than or equal to n then in this case. We could have done 0, I equals 0, I less than n. This way we do 1 to n, we can just print out I or print out I times j. Either approach would have been fine, but this kind of meshes more closely with what we want to print here. There's our I loop. Two-dimensional problem we're kind of solving here. I would just immediately go, let's write up our j loop as well, even though we know there may be more we have to do eventually here. It's a multiplication table, so we do know we really just want to print out for a value of I is 2, j is 3. We're always printing out I times j. Let's give it a go. We could create a separate variable if we wanted to store current value in table and store it as I times j, but we're really not using it for anything else once we've printed it out. So to start with, not saying we're done yet, Let's just print out I times j. Let's enter in a value of 15, and it looks wonderful. Okay, needs work. It's funny. You'll see this a lot in your programs. Mathematically, we're done, right? Our code has done the math that it needs to do, but we're going to spend a lot of time getting it to look good, like to look properly, right? But that's pretty common in programming, right? Your core of what you want to accomplish is already done, and now let's make it look appropriate at the end of the day, which does involve thinking a little bit more about it here. So, okay, couple things. Well, we certainly want to put some spaces between the values. Let's at least do that, right? Let's add a space between values. That is very slightly better. What else do we need to add? I'm open to ideas. Sure. Yep. So another way to, yeah, when j, in this case, equals n, we also want to print an n line. We could do that with an if statement, and that would be valid. If j equals n, also print a new line. The nice thing is we know what happens when j is equal to n. We're done with that inner loop. Let's print it. Well, fine. That's going to look quite a bit better as well. Pray to the replit higher command to give us a working system. There we go. Looking quite a bit better. Spacing is not equivalent. If our value of n is always between 10 and 20, then 3 digits per value is sufficient, right? Because we're going to be between 100 and 400 as our maximum values. I mentioned that briefly in the previous example. If I do %3d, what that says is no matter what the value of I times j happens to be, print it out as with at least 3 bytes or 3 characters. That's going to make it look just slightly more aligned. That helps a little bit. It's already looking quite a bit better. I'm kind of liking that. There's also kind of a column header here as well, right? We want to print out a column header, a column header. That could be for either j or I, doesn't really matter. But in this case, we want to print that out before we've printed out the rest. This probably is deserving of a comment. Print out column header. And that's kind of the same thing. It's printf %3d space, I guess. That's how we did it. And just the value of j with a new line at the end. It doesn't look super swell because there's no like break between the column header and the actual values. So let's print out a separator. Print out a separator row. Here also could be a j loop. And here we want to printf, well, there's 3 integer decimals, integer characters, and a space, so 1, 2, 3, 4, just kind of separators. Again, the math of the code of I times j hasn't changed, and it's not going to change. We're trying to make it look a little bit better. There we go. We got a little bit of a separator. Then we also need to print out row headers as well. So every time we start a new row, so for I equals 1, that's a new row. For I equals 2, that's a new row. We want to actually print out the value. With maybe a little extra separator. Let's print out the value of I. Well, maybe that was a bad idea. That's fine. That adds 4 spaces at the beginning of every line. So on that new line, we have to add it. For the separator row, we also have to then add it. And then we don't need it. And I feel like we're off by one. What do you guys think? Because it's percent d pipe with a space. We need 5 to space it out. We have a nice little multiplication table. You can take a look at this code offline on your own and look at our beautiful multiplication table. Let's leave things here for today. As always, test your code with crazy values and see what happens. Needs work. On Friday, we'll talk about variable scopes, which is pretty important as we write more complex looping structures. Enjoy.